Something unusual is happening right now. Earth is experiencing an unexpected wave of close asteroid flybys this September 2025. One asteroid, named 2025 RJ2, came extremely close, less than 300,000 kilometers from Earth. Another, 2025 FA22, is expected to pass us at just over twice the distance to the Moon. Over just 1 week, astronomers have tracked dozens of smaller space rocks flying past Earth at distances even closer than the Moon. At the same time, a strange interstellar object called 3I/Atlas with a unique chemical makeup is racing toward Mars on a never-before-seen trajectory. The numbers are surprising. Statistically, this kind of activity shouldn't be happening all at once. So, is this just random, or are we witnessing something more serious that could change how we prepare for threats from space? The question is more important than ever. This month's wave of warnings is unlike anything seen before. According to astronomers at the Minor Planet Center, asteroid 2025 FA22 will pass about 835,000 kilometers away, roughly 2.2 times the distance from Earth to the Moon. But just 3 days earlier, RJ2 came much closer, about 300,000 kilometers, which is less than one moon's distance. These events aren't completely unheard of, but the sheer number is. Between September 12 and 18, a record-breaking 28 near-Earth objects flew past us within the Moon's orbit, 3 times more than the previous weekly record. Most of these space rocks are relatively small, between 8 and 25 meters across. They're big enough to cause an airburst in the atmosphere, like what happened in Chelyabinsk, Russia in 2013, or they could simply burn up harmlessly. But 2 of them, FA22 and RJ2, are much larger, possibly up to 120 meters wide, and that makes them a real concern. Global observatories are constantly on the lookout. Telescopes in Hawaii, Pawn Stars, Chile, Atlas, Arizona, Catalina, and the Rubin Observatory in the Atacama Desert are all scanning the skies. These telescopes feed massive amounts of data into software that detects fast-moving objects, sometimes within just hours of spotting them. The Rubin Observatory, which only recently began full operations, is already playing a major role. Its wide field camera can sweep across large areas of the sky and spot objects that might have gone unnoticed just a year ago. Statistically, this kind of asteroid cluster shouldn't be happening once in every 10 years. Models that account for observational bias say the odds of spotting more than 25 sublunar near-Earth objects in a single week are less than 1 in 1,500. That makes this September spike stand out even when you factor in better technology. Some scientists credit advanced detection systems, while others wonder if something more is going on, like gravitational patterns or even an unnoticed asteroid breakup event. Right now, we can detect over 90% of objects larger than 20 meters that pass within 1 lunar distance. There are still blind spots, especially from the direction of the sun, but they're shrinking. Chelyabinsk taught us one of the biggest blind spots in asteroid tracking: objects that approach from the direction of the sun, making them nearly invisible to ground-based telescopes until it's too late. Sergei Karpov, whose dashcam footage of Chelyabinsk became world famous, later described the aftermath as full of confusion, shattered glass, and panic. Today, he works with emergency teams to help cities plan for surprise disasters. His message is simple: most people don't understand how small the line is between a harmless fireball and a disaster that could flatten an entire city.
After each close pass, scientists run computer simulations, and the numbers are always striking. Everything from the time of day to how many people live nearby can affect the outcome of an impact. There's no intent behind it. It's just physics playing out in space. The only real protection we have is staying alert, detecting threats early, and turning that data into action. When those systems fail, the cost isn't just numbers. It's lost lives and destroyed communities. Then there's Swan, a comet that caught scientists off guard. On September 11, 2025, a spacecraft instrument called Swan, part of the SOHO satellite, picked up signs of a new comet, not through a telescope, but by detecting a sudden burst of hydrogen in space. This hydrogen glow, invisible to the human eye, showed up in ultraviolet data before anyone on the ground had even noticed the comet. Backyard astronomers began pointing their scopes toward the Virgo constellation. Within a single night, Swan's tail doubled in length and the comet started to brighten quickly. Spectroscopic analysis revealed that it wasn't just light, it was carrying large amounts of hydrogen along with traces of carbon compounds and cyanogen. As the comet moved closer to the sun, the rate of gas release, known as outgassing, skyrocketed. Even seasoned astronomers were surprised that hydrogen levels far exceeded water vapor, suggesting the comet was breaking apart from the sun's heat. With each new crack in its icy core, more hydrogen was released and picked up by ultraviolet instruments. This activity triggered an urgent response from observatories around the world. The Rubin Observatory, still fine-tuning its operations, used emergency time to monitor the comet's behavior. Meanwhile, amateur astronomers contributed real-time data, tracking changes in brightness, tail shape, and timing sudden outbursts. Thanks to these rapid reports, high-powered telescopes were able to capture valuable details, like jets of gas shooting from the core and slight chemical shifts, signs that the comet was under stress and might soon break apart. As September progressed, new models suggested that Swan's fragile core might not survive its closest pass to the sun. If it shattered, it could create a spectacular light show visible from both Earth and space. But for planetary defense experts, Swan was more than just a pretty sight. It served as a sharp reminder: not all cosmic threats follow predictable paths. Sometimes, the first sign of danger is just a brief flare of hydrogen. That's why there's now a global network of professionals and hobbyists watching the skies every night. And with April 13th, 2029 already marked in red on every planetary defense calendar, no one is taking chances. Apophis will be visible to the unaided eye as it moves across the sky on that day, passing only 32,000 kilometers from Earth's surface, closer than many communication satellites. Apophis, a supposed planet killer that was initially discovered in 2004, was the subject of doomsday headlines for years. Since then, however, the threat of impact has diminished in favor of a unique scientific opportunity: a live planetary defense practice with the world watching and the necessary equipment. There's more to the near approach than just a show. Apophis will be pulled by Earth's gravitational pull, which will increase the tides of rubble and dust rather than water. Scientists anticipate actual changes, such as landslides on the surface, loosening regolith, and possibly even a change in the asteroid silhouette. On a body of big, these tidal effects have never been closely measured. There's no way to replicate this natural experiment in a lab. NASA has sent OSIRIS-APEX, a probe designed to meet up with Apophis shortly after the flyby in order to capture it. Its purpose? Keep track of every scar, every rock that has been moved, and every indication of Earth's unseen pull. The before and after photos will show how asteroids react to near-close encounters and how a stray rock can be redirected by slight gravitational pulls. The strategy has personal significance for Andrea Riley, a systems engineer on the Hera team. She writes of her teenage fear at seeing Apophis dominating the headlines in a 2023 journal entry. Her work is now driven by that feeling of fear, which has been softened by the promise of new technology. Apophis is not just a test for spacecraft and scientists. Humanity's capacity to track, simulate, and, if necessary, fend off an actual attack is being practiced. Every computation, observation, and line of code created for ground-based radar or OSIRIS-APEX is a step closer to a time when near misses are handled with cool accuracy rather than fear. The globe witnesses planetary protection in action as Apophis speeds by, transforming a once fearful headline into one of readiness and exploration. From the first spectrum, 3 I/Atlas identified as C/2025 N1 stand out. Its hyperbolic trajectory was flagged by Pan-STARRS on July 1st, but the chemical fingerprint was what made scientists race to get time on the biggest telescopes in the globe. As the comet moved through about 4.4 astronomical units, early VLT-X shooter data showed a coma that was dominated by carbon dioxide rather than water vapor. The figures are verified by JWST in August. Water produced only 6.6 kilograms of carbon dioxide per second, significantly less than carbon dioxide's 129 kilograms. That is an almost 20-to-1 ratio that has never been seen. In contrast, most comets in the solar system have the opposite ratio, with water outgassing dwarfing carbon dioxide. The normal rules are inverted here. The volatiles are not the only abnormalities. A strong atomic nickel signal, 4.6 grams per second flowing from the coma as of August 21st, was seen in high-resolution spectra from the VLT's UVES instrument, which were collected across a number of nights in July and August.
However, iron, which in cometary chemistry is a nearly constant companion to nickel, was not present and was below the detection threshold. Even among interplanetary travelers, this nickel without iron pattern is uncommon. Due to the same heating processes, nickel and iron typically occur together on comets in the solar system. Theories cover everything from the selective loss of iron over billions of years adrift between stars to the special chemistry of creation. Some suggest that more volatile iron compounds are being stripped away by cosmic ray weathering, while others suggest that nickel-rich organics are breaking down. Although there is currently no one model that matches all the facts, the discussion is heated and continuous. Another surprise arrived in the middle of August. A sudden flare was detected by the Mars Reconnaissance Orbiter, which was scanning ultraviolet wavelengths, an eruption that, in less than 36 hours, quadrupled the comet's brightness. The tail separated into several parts, with dust streaming in different directions, according to photometry taken from the ground. The typical water-driven jets don't match these sporadic outbursts. Rather, they suggest that as sunlight enters new fissures, pockets of carbon dioxide or other volatiles will emerge. The puzzle is augmented with rotation studies. Analysis of the light curve points to a sluggish, perhaps tumbling nucleus that rotates on a time-varying axis. With very slight variations in brightness, the span extends over 22 hours. Evidence of a complex, non-principal axis rotation or a roughly spheroidal form, this further complicates the prediction of tail evolution and explosions. With perihelion scheduled for October 29th, spectroscopists around the world are engaged in a race to capture every detail before the comet vanishes behind the sun. Every new dataset adds another level of interest. 3I/Atlas is still a chemical anomaly for the time being, a slow-moving message from a darker, colder region of the cosmos.